Welcome to This Explainer. Look, we hear the term AI everywhere today. I mean, literally everywhere, from the evening news to the smartphones sitting in our pockets right now. But what is actually happening under the hood? Today, we're going to peel back the layers of artificial intelligence to understand exactly how machines learn and reason. Because once you get past all the hype and the buzzwords, you'll see it's just this incredibly fascinating world of mathematics, logic, and engineering.
Okay, here's our roadmap for today. We're going to hit 5 key areas: decoding artificial intelligence, the core goals of AI, how AI makes decisions, the machine learning revolution, and finally, inside artificial neural networks. We are going straight from the big picture of what AI actually is, all the way down to the exact mathematical architectures making it all work.
Let's just kick things off right away with Section 1, Decoding Artificial Intelligence, or the Big Picture.
We throw the acronym around constantly, but let's actually define our core subject here. Basically, artificial intelligence is the capability of a computational system to perform tasks that we usually associate with human intelligence, things like learning, reasoning, and problem solving. It's really important to remember that AI is fundamentally an engineering, math, and computer science field. The whole goal is just enabling machines to perceive their environment and maximize their chances of achieving defined goals. It is not magic. It's not a brain floating in a jar. It is highly structured mathematical problem solving. And you know, it absolutely was not an overnight success. The field was actually founded as an academic discipline way back in 1956. But following that initial burst of hype, researchers had to endure what are notoriously known as AI winters. These were decades, literally decades, of severe funding droughts because the early tech just couldn't match the incredibly lofty promises being made. The real turning point? That didn't happen until 2012, when graphics processing units, GPUs, finally started accelerating neural networks. That massive leap in compute power was followed by the introduction of the transformer architecture in 2017, which, as you probably know, directly paved the way for the massive generative AI boom we're living through in the 2020s.
Which brings us to Section 2, the core goals of AI, or, as I like to think of it, how we go about teaching rocks how to think. So now that we know what AI is, what exactly are computer scientists trying to replicate from the human experience? Well, to make any real progress, researchers had to take this massive, fuzzy concept of intelligence and break it down into specific, solvable subproblems. They needed machines to tackle reasoning, knowledge representation, and planning. But they also had to conquer machine perception. Think about how a self-driving car physically sees the road, and natural language processing, which is what powers the virtual assistant on your phone. They're even working on social intelligence now, like recognizing human emotions. It's really all about conquering the idea of intelligence piece by piece.
And when we talk about achieving these goals, we really have to draw a hard line between two levels of success. On one side, we have narrow AI. This solves very specific subproblems, like playing chess or translating a language. It is absolutely crucial to note that every single AI tool you use today, no matter how impressive it seems, is narrow AI. It's just incredibly good at one specific thing. On the other side, though, is artificial general intelligence, or AGI. This is the holy grail. Companies like OpenAI and Google DeepMind are actively chasing AGI, a system that can complete nearly any cognitive task, at least as well as a human, with full across-the-board versatility.
Which naturally leads to a pretty fascinating pivot for us. How do we actually teach a machine to think? We've got these lofty goals, sure, but how do we get from the theory to the actual computational techniques?
Let's explore exactly that in Section 3, How AI Makes Decisions, by opening up the toolbox of logic and search.
Long before we had modern chatbots, early AI relied on highly structured, rigid methods to navigate the world. A primary one was called state space search. Just imagine a machine searching through a massive, branching tree of possible states to reach a goal. The problem here? Well, if you try to map out every single possible move in a game of chess, the number of choices grows to astronomical numbers almost instantly, causing the whole system to just slow to a crawl. To get around this, machines needed heuristics, basically computational rules of thumb. Think of it like deciding to sacrifice a pawn to take a queen. The machine doesn't actually need to calculate every move to the very end of the game to know that's generally a fantastic move. This heuristic approach prioritized the best choices and massively sped up the search process.
There is such a fascinating contrast between that early AI and what we use today. Those early systems relied on classical step-by-step logic, but as we saw, it was slow, it required absolute certainty, and it was super prone to what we call combinatorial explosions, meaning the math just got way too big, way too fast. But the real world is messy and uncertain, right? So AI evolved to use probabilistic guessing. This is fast, it handles uncertain environments beautifully, and it uses expected utility to make decisions based on the highest probability of a good outcome. Essentially, it closely mimics the intuitive, rapid judgments that you and I make every single day.
That vital need to handle uncertainty ushered in our next major era. Here's Section 4, the machine learning revolution, focusing on programs that actually improve automatically.
Broadly speaking, there are three core ways these machines actually learn. First, in supervised learning, the machine is essentially spoon-fed labeled training data. It's like showing it 1,000 flashcards clearly labeled cat. Unsupervised learning is a totally different beast. The machine is thrown into massive streams of unlabeled data and forced to find the hidden patterns entirely on its own. And finally, there's reinforcement learning. This is a strict trial-and-error approach, honestly, a lot like training a dog. The AI agent learns to make decisions over time by being rewarded for good responses and punished for bad ones. And these new learning types completely supercharge specific fields, especially natural language processing, or NLP. Empowered by machine learning, models didn't have to just follow basic grammar rules anymore. They started using word embeddings. Imagine taking a single word and assigning it a very specific mathematical coordinate in space, based entirely on its meaning, so words with similar meanings are grouped physically closer together in the math. When you combine that with those transformer architectures we mentioned earlier, that is the exact technology allowing models like GPT to read, write, generate totally coherent text, and literally pass the bar exam, all just by finding statistical patterns in language. So, what is the actual engine driving this deep learning revolution? Let's look under the hood in our final part, Section 5, inside artificial neural networks, where we mimic the human brain. The real engine powering modern AI relies on a powerful biological metaphor. An artificial neural network is basically an interconnected group of nodes, we call them artificial neurons, that loosely model the vast network of real neurons in a biological brain to recognize patterns. Signals are passed through these artificial nodes, applying mathematical weights along the way, which is surprisingly similar to how biological neurons fire in your own head to process information. And here is how that network actually learns in a continuous cycle. First up, the input layer receives the raw data. Second, this data moves into the hidden layers, which apply all those complex mathematical functions and weights. Third, and honestly, this is the really clever part, a backpropagation algorithm steps in. It acts a lot like a coach correcting a tennis player's swing. It actually adjusts those mathematical weights backwards through the network to minimize any errors in its guessing. Finally, step 4, the output layer delivers the prediction or classification. The network just continuously tweaks its internal weights through this exact cycle until it accurately identifies the pattern. You hear the term deep learning constantly, right? It sounds incredibly mysterious, maybe even a little sci-fi. But actually, scratch that, it is incredibly literal. For a neural network to officially be considered deep, it literally just needs to have at least 2 hidden layers nestled between the input and output layers. That's it, 2. It's simply a measure of the architectural depth processing your data. And of course, researchers don't just rely on one single type of network. They build highly specific architectures for specific tasks. For instance, feed-forward neural networks are super simple. Signals just pass straight through in one direction. But recurrent neural networks, specifically things called LSTMs, actually feed signals back into themselves. This gives them a really useful form of short-term memory that is absolutely perfect for processing streams of text, like the predictive typing on your phone. Then you have convolutional neural networks, or CNNs, which process local visual patterns, making them the total backbone of things like facial recognition and modern computer vision. So as we wrap up this explainer, we really have to look to the future. We've seen how AI evolved from these rigid, slow logic trees into massive, deep neural networks capable of just astonishing feats of probabilistic pattern recognition. But we are left with a pretty massive question to ponder. As these deep learning models grow increasingly complex, how far are we, really, from closing the gap between the narrow AI of today and true artificial general intelligence? When will these computational systems finally match the full versatility, nuance, and breadth of the human mind? Because the architecture is there, the computing power is growing exponentially, and honestly, the answer might arrive a lot sooner than we think. Thanks for exploring the highly structured world of artificial intelligence with me today.